Up to this point, when it came time to integrate, all that we have been able to do is look at the problem and say, does this look like something that we've taken the derivative of? Does this look like the answer to a derivative problem? And that works on occasion, but that is not going to get the job done for most integrations. So what we're going to see here is the first actual integration technique. Happens to be my favorite. Anytime I'm asked to integrate, the very first thing I do is I look at it and say, can I use U substitution? Will U substitution work? Because when it works, it's quick, it's easy, it's effective. Now, be aware that as we learn in the future other integration techniques, that it is quite common with an integral to have to use one technique within another, within another, within another. You may have to stack those techniques one on top of the other to get an integration problem completed. All right, but for now, let's take a look at U substitution. With U substitution, what you're actually doing is, contrary as it may seem, you are adding an extra variable to the problem for the purposes of simplifying the problem. All right, U substitution says that if you are integrating f of g of x, g prime of x with respect to x, again, notice that we have a function within a function, and then here the chain rule has been used. All right, if you're integrating that, then you can simply integrate, more simplistically, you can integrate f of u du, where the u plays the role of the original g of x. All right, so in other words, when you're doing U substitution, what you're looking for is you're looking within that you are integrating and saying, is there something here whose derivative is also here in a product type arrangement? In other words, if there's a function within whose derivative is also present, you can use the U substitution. All right, an example. If you look here, we are integrating a product. We actually have multiple products here. This is 2 times x times the square root of 1 plus x squared. And again, what we're looking for is there something here that I can take the derivative of that will take the place of another part of the product? And if you look at first glance, hopefully you notice that the derivative of x squared is the 2x. So there is something here whose derivative is sitting right here. All right, that might tempt you into thinking, and you would be starting down the right track. That might make you think that u should be x squared. But with the U substitution, we want to take as much out of the problem as possible with that U substitution. And notice that if you include the 1 plus, then when you take the derivative, you still get the derivative of this is still the 2x. So that way I have removed a little bit more of the problem, simplified the problem a little bit further without messing up my objective. And again, that objective was to take care of this 2x right here. All right. So what you'll do is you now know what u is. We need to know what du is equal to. And again, differentiating both sides, du would be a 2x dx. Now, something that not everybody does, but something that I'm in the habit of doing, is since the dx is what's in the problem now and it needs to be replaced, I solve for it. I get the dx is a du over a 2x. So coming down with this problem, here's the integral, here's the 2x, here's the square root, but everything that's under the square root now has been simplified down to nothing but a u. And the dx is equal to a du over a 2x. And what we wanted to see happen was not just a simplification, but a complete removal of the x variable. And you'll notice that happens. So this can be written as u to the 1/2 power du. Integrating, remember that when you integrate, the power goes up by 1, so that becomes a 3/2, and you divide by the new coefficient, which is the same thing as multiplying by its reciprocal. And always remember your constant of integration. All right, so thus far, the integration's complete. But the original problem was an x problem. I've got an answer that's written in terms of u. Can't leave it like that. So I go back and I undo the substitution, take out the u, put back what it was originally stated to be equal to. And at this point, technically, if you wanted to get really, really technical, that's a different constant. Okay, technically speaking, it would be good to put in a different constant. A lot of books don't even bother with that, since this is an indefinite integral. They don't much bother with that. They assume that the constant you end up with here was the x constant from the original. So, I mean, technically, that's not a big deal. Just as long as you remember a constant of integration, you'll be okay. All right? So, let's try that again. The challenge to use substitution is looking at it and spotting what's here that will play the role of the u. All right, so what's here? Now we have integral of an x over an x squared plus 1 quantity squared dx. Again, the question becomes, what's here whose derivative is also here? Well, if you were to let u equal to the x squared, the du would be a 2x. We don't have a 2x. We have just an x. Be aware that if you're off by a constant, it's not a big deal. All right, if you have a 2 where you didn't need one, or you needed a 3 and you didn't have one, it doesn't matter. We will fix that very, very easily. Also remembering, grab everything you can. If I can take the plus 1 and get it out of the problem, that's an improvement, all right? Because du will still be a 2x dx. And again, I have a 2x here and only an x there. Close enough, not a problem, all right? I also have the dx is du over 2x. So back to the original problem, all right? This becomes integral of x over, the denominator is now nothing more than a u squared. The dx comes out, and you're left with a du over a 2x. The x's cancel. And what about that 2? We had a 2 that we really didn't want. Well, I'll just throw it out front. Constants can be thrown out front. That's why if you're off by a constant, it doesn't matter. Easy fix. 1 over u squared, I would probably choose to write that as u to the negative 2. And now I can integrate. There's my 1/2. The power of u bumps up by 1. And divide by it. Get your constant of integration. This becomes a negative 1 over 2u plus the constant of integration. And the way that happened was the u to the negative 1 went to the bottom, became u to the positive 1, and the 2 was already there. Put back what u is equal to. And again, technically, it's a new constant of integration, but that's not a really, really big deal, right? Let's look at some more. Let's look at some more of these. Turn this over, try and conserve a little bit of paper. What if I had the integral of e to the power cosine of t times the sine of t dt? All right. U substitution doesn't work, of course, with just an x variable. All right, again, is there something here whose derivative is also here? Well, if you let u equal cosine of t, then the derivative of u is negative sine of t dt. I'm off by a sign here, okay? There's a negative here that I didn't want. Not a problem. I'm not worried about it. I can deal with that. My dt will be a du over a negative sine t. Plugging back in, this becomes integral of e to the, now it's just a u, and then you have times a sine of t. dt comes out, and you get a du over a negative sine of t. Sine of t cancels sine of t. A negative comes out front. And that's easy to integrate. Probably one of the easiest integrals you'll ever encounter. Plus the constant integration. And then you put the u back. Right. Again, with u substitution, the trick is what's here, whose derivative is also here. All right, that's what you have to spot. Those have been fairly obvious, I think. It's not always that obvious. It's not always that clear. For example, if we had the integral x over 1 plus x to the fourth dx. Yep, that's a dx. All right, with this one, it's more subtle. The derivative of x to the fourth is not x. Okay, it's a 4x cubed. Being off by 4, again, as we said, it's not a big deal. But the x cubed, that's a problem. That's not easy to remedy. All right, so there are patterns you need to learn to look for. I'm going to rewrite this like so. All right, u to the x to the fourth is just x squared squared. And the reason I did that, a couple of different things, a couple of different motives. The derivative of x squared will have the x in it. It'll be a 2x. I'll be off by 2, but I don't care. I can fix it. And plus 1 over 1 plus a square in the denominator of a fraction is a pattern you need to learn to look for. Okay, you need to learn to spot that pattern. So I'm going to let u equal just the x squared this time. This time, I can't bring in the 1. It just won't work. There's no way to incorporate that 1 into my u. So du will be a 2x dx. That makes dx equal du over 2x. It seems like we're getting 2x's a lot, but it's the way it's working out. This becomes integral of x over 1 plus a u squared. And forgot the dx momentarily. In place of the dx, I get a du over a 2x. Again, x's cancel. Again, a 1/2 goes out front. And if you're thinking, well, that integral doesn't look any better, actually, it's a lot better. This is a pattern you need to learn to spot. That's 1/2 arctan of u plus a constant integration. Derivative of arctan is the 1 over 1 plus variable squared, and you've got to learn to spot that pattern. It gets used pretty heavily. So it's 1/2 arctan of an x squared, and again, on a very technical note, plus a different constant integration. I probably should knock that off for the time being. It's not going to matter much, but there it is. All right, so again, with these, you've got to learn to look for, those patterns. All right, so with that in mind, let's switch over to some definite intervals. All right, this technique of integration can be used with a definite integral. And when you do it, you can evaluate 2 different ways. All right, there's two different ways to evaluate that I wanted to show you. So let's do this. Let's say I had the integral from 0 to square root of pi of an x times a cosine of an x squared dx. For this one, oh wow, is this going to come up again? Okay, I'm going to let u equal x squared because du will be the 2x dx. The dx will be the du over the 2x. Going to have this 2 in there again. Oh well, I'll try and find something without a 2 in it next time. All right, so this becomes the integral of, all right, and I'm going to leave the 0 and the square root of pi off just for a moment for a reason. Okay, here's an x a cosine of a u, and in place of the du, in place of the dx, you get a du over a 2x. The x's cancel. 1/2 goes out front, and we get a cosine of u du. All right, and the reason I left off those limits of integration is because the 0 and the square root of pi, those are limits of integration for x and x only. All right, so if you're going to do this problem and you're going to use the u's, then what you would have to do is say, well, if u equals x squared, then when x is 0, right, 0 squared will be a 0. And when x is square root of pi, then u will be square root of pi squared, which is just pi. In other words, if you switch over to u and you want to stay in the variable u, you have to switch your limits of integration. You have to take the x values that were here, plug them there, and find out what the u values would be. So this would be a 1/2. Integral cosine is sine of u evaluated from 0 to pi. All right, and I'll leave the evaluation up to you. That should be an easy one for you to handle. All right, an alternative to that, all right, alternative ending to this story would be 1/2 integral cosine of u du being a 1/2 sine of u. And if you take the u out and put the x squared back in, you can then evaluate from 0 to square root of pi. All right, so in other words, if you remove the u and put x's back, you can use the original limits of integration. If you decide I'm not going to bother to remove the u and put the x's back, then you have to come up with new limits to your integration by plugging in right here. All right, so again, that will work either way, always will work either way, but you just have to remember to either to switch or not to switch. Okay, all right, so as promised, let me see if I can find something that doesn't have an x squared turning into a 2x. All right, let's find something a little bit different. It seems to be popping up a lot. All right, okay, here's one where that won't happen. If you have the integral of e to the z plus 1 over e to the z plus z, integrating with respect to z, integrating from 0 to 1, what you would choose for that is so that u equal e to the z plus 1, so that du was just a, oh, wait a minute, that's the wrong one, got it backwards. E to the z plus z, when your derivative will go e to the z plus 1 dz. Yep, now that works better. So that dz is equal to a du over e to the z plus 1. Yeah, that falls into line a lot better. So integral from wherever to wherever of e to the z plus 1 over a u, and du over e to the z plus 1 takes the place of the z. That cancels. So again, notice I'm leaving off the limits of integration. I'm leaving them off because here's what I'm going to do. When I integrate, what I'm integrating is 1 over u, which is natural log as the value of u. Notice I'm not putting a plus c on here because this is a definite integral. All right, and no, there's no plus needed. Okay, just equal to natural log of absolute value of e to the z plus a z. All right, and that I'm going to evaluate, I would evaluate from 0 to 1. Why can I now evaluate that from 0 to 1? Because I took the u's back out of the problem, put the z's back in, so I can go back to my original limits of integration, which is what I typically like to do. That's the way I prefer to do it. All right. All right, so again, with substitution, what you have to look out for is what's here, whose derivative is also here, and make the substitution accordingly.